Our speaker today is a friend of mine, an old friend of mine, Parke Kunkle. Parke earned his master's degree in physics from the University of Minnesota, and then he started in on a teaching career that spanned 48 years, and he ushered more than 6,000 students to the former Minneapolis Planetarium. He earned several Teacher of the Year awards at Minneapolis College, teaching astronomy, physics, computer programming, engineering, and mathematics. That's a lot. Parke has been a guest on both local and national media discussing astronomical events such as constellations, planetary alignments, and the zodiac. He is a member of the Minnesota Astronomical Society, a founding member of the Minnesota Planetarium Society, of which we both belong to, and served on the advisory board of the Bell Museum of Natural History. His proudest achievement is bringing a new planetarium to the Twin Cities. He encourages everyone to see the wonders of the universe in the planetarium at the Bell Museum, located on the St. Paul campus of the University of Minnesota. So please welcome Parke Kunkle, also known as Sassy Astronomer, and he will be telling us about the amazing James Webb telescope.
Does that work that way? No, I look more like an astronomer, I think, in that case. Thank you, Peggy. Really appreciate that. Can you see that all right? Okay, or can we turn the front one off? Anyway, just have to do some little spiel about the Bell Museum. There it is, just opened in 2018. This is Minnesota's Natural History Museum. And we were fortunate to get the Macmillans to donate to put a new planetarium in the Bell Museum. And in that Bell Museum, there are a number of exhibits. And this is the area that puts Minnesota's biomes in context. So it talks about planet Earth and other planets and how life can possibly develop. But this, in part, is the work of Peggy and Ilo. And so I just get, thank you. Great stuff. So yes, we've got a new planetarium, really good exhibits in the Bell Museum. Go over and see it. It's really good. So how does the Rotary come into that? In 2006, when we had torn down, not us, but some others had torn down the old planetarium, Peggy and I and others were working to get a new planetarium built. And so in 2006, we were here at the Rotary talking about the new planetarium. And we got something like 15 new memberships, plus some donations for the planetarium. That was one of the sort of, for me, was one of those exciting times that said, okay, we're out here doing the right thing, and that there are people that are willing to help do this. So you guys are my favorite Rotary right here. That's great stuff. Okay, I'm here to talk about the James Webb Space Telescope, just launched recently. I love this picture because these kids built a full-scale model of the James Webb Space Telescope. So you can see it's about the size of a tennis court. One of the remarkable things about this is, well, there it is with a little bit more of the technical stuff on it. Here's the mirror. So light comes in this way, always from the right-hand side. That's not true. This thing can turn. Okay, comes in here, hits these mirrors, comes back out to the secondary mirror, and then goes through this hole into the scientific instruments behind it. Those mirrors are about 6.5 meters across. So roughly the size of about half the room here. This is way out about 1 million miles from Earth, and it needs to be very cold in order to sense the infrared radiation. And so you've got to shield it from any other light, especially the sun's light, even being 94 million miles away you still need to shield it. So these are 5 layers of material to try to shade this instrument. And I don't want to talk about the technicalities of it because there's so many good pictures to look at. So if you have questions, I'll be happy to answer those later on. But one of the remarkable things about that is, how do you launch a tennis court into outer space? Rockets aren't that big, right? So you've got to fold this thing up, make origami out of this thing to fit in the nose cone. And then once you launch it, you've got to unfold it. And there were something like 334 failure points. So a bolt that wouldn't release, or a mylar sheet that wouldn't pull out correctly, all of them worked. It's absolutely amazing engineering that happened. So what's JWST all about? Its goals are small, right? Just investigate the origins of the universe, galaxies, stars, and life. That's it. Okay, here was the first picture released from the James Webb Space Telescope. And what do you notice? Don't worry about what it is. Just what do you see?
Different colors?
Yeah, different colors.
Incredible numbers.
Numbers, yes.
Streaks.
Yeah, stars with spikes coming out of them. Streaks. Yeah, different sizes. Exactly. Different shapes. Yep. Yeah. This is quite a remarkable picture. When I first looked at it, this is, by the way, it's called the Webb Deep Field Image. So what they did was to look at one area of really dark sky and look at it for a few minutes and say, what can we see there? And that's what they got. Just incredible. When I first looked at it, I said, oh, that looks like the Hubble Deep Field Image. The difference is that with Hubble, it was like looking through a tube of toilet paper or something like that, right? That big a sky. Webb is looking through a straw at that same kinds of area. And Hubble took about 2 weeks to get a picture like this. These guys did it before breakfast. No, just quite remarkable of what they're getting. So they're seeing much, much deeper into space. So what are we seeing here? All right, these spiky things, those are all stars that are in our own galaxy, so very nearby us. They're just really bright, and I won't get into the physics of the spikes at all. So that's that. These fuzzy pieces right here, sort of in the middle of the picture, and we'll see why those are important in a minute, are a set of galaxies about 5 billion light years away. Okay, let's ponder that for just a minute here. Supposing I took my little laser pointer here and shined it that way, right? And let it go and bend it around the Earth, okay? It's hard to do, but supposing I could do that. Play with me here. All right, so bend it around the Earth. That beam would go 7.5 times around the Earth in 1 second, okay? 7.5 times around the Earth, and that's how fast light is traveling. 186,000 miles a second. That's amazing. Okay, now let's think about this. The moon is about 2 light seconds away. Light from the moon takes 2 seconds to get here. Sun, about 8 light minutes. Okay. Well, wait a minute. Does that mean we're seeing the sun as it is or as it was 8 minutes ago? Okay. It's just quite a, that always blows my mind when I think about that. Okay, those galaxies, 5 billion light years. That light's been traveling for 5 billion years at 186,000 miles per second. That's amazing. So if you can't sleep tonight, think about that just a little bit. Quite remarkable. These arcs, I'll say more about those in just a minute. Some of these galaxies are relatively nearby, but some of them, especially the odd-shaped ones, are much further away. And there's some here that I can't really even see. mean, if you look right there, I'm going to show you that and close up, a little closer up in a minute here. But lots of galaxies, very, very distant. So I need to talk a little bit about wavelengths here. Visible light, that's what you and I see all the time. And it's part of all these different kinds of waves: gamma rays, X-rays, ultraviolet, visible, infrared, microwave, and radio waves. So they're all the same thing, just different wavelengths. So peak to peak here, that would be a wavelength. Same stuff. If you get longer wavelengths, then you're coming down here into the infrared region, and that's where JWST is working in those infrareds. We'll see why in a minute. You all know about many of those others, so I won't waste time there. Hubble was designed to look in the visible region and a little bit in the infrared, ultraviolet region. So it cannot see the infrared stuff that JWST can see. All right, so if we took a small telescope, maybe a 12-inch kind of telescope, and looked in the southern hemisphere, we could see this nebula, the Carina Nebula, 7,500 light years away, so nearby. Okay, we can see that thing. But why do we use IR? A little piece of that Carina Nebula is the left-hand picture there, taken with Hubble and using visible light. And what you see is a lot of gas and dust, and there's stars forming in the gas and dust. But here it is, same picture with infrared. And notice the differences. Okay, a lot of the gas and dust you don't see, but look at all the stars that show up. They're here, they're just blocked by the gas and dust. But infrared gets through the gas and dust. And so we now can see these. The other part about that being so important is that we're certain that stars, when they form out of these big gas clouds collapsing. And as they're collapsing, they give off infrared radiation before they're even stars. So in essence, a lot of these dots over here are newly forming stars. They haven't become a star yet, but they're on their way. And so we're studying the birth of stars, JWST, origin of stars, kind of thing. So lots of interesting material. A little bit closer even, same nebula, Carina Nebula. And again, with the infrared, we can see all these stars that we would not see just using visible light. Okay, why else infrared? I can see the smoke pouring out of people's ears at this point. Michelle, you had
I'm wondering, do the lights, the light from one star or something potentially block another? Would this allow more visibility of all of them?
That's a really good question. Let me back up a couple of slides here to these. For example, these pillars that you're seeing there are because right up in this part that you can't see, there are some hot young stars. And hot young stars blow off a lot of ultraviolet radiation, which blows this material away. And so there's a battle going on here. There's a star forming right there in the tip of that thing. Will it form before those hot young stars blow the material away or not? Stay tuned. Yeah. So good questions. All right. So what's this all about? Expansion of the universe, stretching visible wavelengths, red light left has now become infrared. I'll try to explain that to you in just a second. But before we do that, let's do a little demo here. So you've all got little slides on your table there, right? And let me turn my little light on. There we go. Keep going. A little bit brighter. All right. What I want you to do, well, first, yeah, hold it up and look at the window maybe or something like that. What do you see? A lot of colors, right? You can see the, right? Yeah, rainbow spectrum. This, what you've got is called a diffraction grating. It's a lot of little lines on that thing. You can't see the little lines because they're so close together, but it acts like a prism. It separates the colors out. So now take a look up here at this. What do you notice? Look off to the one side, not maybe directly at it.
A lot of rainbow.
A lot of rainbow, individual lines, maybe. Okay, we're used to seeing rainbow, a nice continuous one color into the next. Here, we're seeing individual colors. Okay, this is what we call the spectrum of this particular light. And when you see those individual lines, you know it's a gas that's in there, not something like a tungsten filament light bulb. So that's a gas that's in there. Okay. All right. So I know I'm hurrying through this, but there's so much to tell you about. Let me put this back up here. Michelle, I noticed you used my little piece of cardboard there as a holder for the computer. It's perfectly okay. All right, we could talk more about that. Happy to hang around. Those things, by the way, cost me about $2 a piece. If you want to take one with you, you're happy to do that. Put $2 in the happy jar. Okay.
Good job.
All right. So what's the spectrum stuff all about, and what does it then tell us? Well, here's the spectrum. Remember that little dot that I was trying to point out? There it is, right there. There's those fuzzy galaxies, and so forth. When JWST was able to take a spectrum of it, you can imagine 13 billion light years away, all right, it saw these lines, just like you saw the lines in that spectrum, and that tells you what elements are there. So they could tell there's oxygen and neon and hydrogen and so forth in the spectrum of that galaxy, which I think is remarkable. You know, it's hard enough to show you the spectrum here in the room, but 13 billion light years away. Wow. That's
all of those would be in a galaxy.
Yes, not the spiky ones. That's in our own galaxy. But everything else is in a galaxy. And so this is the spectrum of that galaxy. Yeah, of probably billions of stars all in one area. Yeah. It's quite.
It took 13 billion years for that light to get here.
Yes.
Is it still there?
That's a really good question that you're going to have to sleep on. Those, I mean, it's possible that those combined to form our own galaxy. We might be looking at us as a precursor. So your question is well taken. That's what it looks like 13 billion years ago, but not now. Define now. Great question. Yeah.
But like an exposure of about 100 light years away. With exposure that could swallow up the Earth from possibility.
Yes and no. Okay. If there were something that were ready to explode that was 100 light years away, then yes, it would definitely affect Earth, like a supernova, for example, an massive exploding star. But there aren't any. So you can relax on that one. Probably we're looking at something that's maybe 1,000, 2,000 light years away. That would be about the nearest possibility. And then as long as that beam of gamma rays doesn't come right at us, we'll be okay. There's other things to worry about. Exactly. Exactly. Good. Okay, so what can we do with that spectrum? All right, here's 4 different galaxies. Okay, all there, and so forth in those locations. And there are the spectra of those galaxies. Okay, And you notice they all look the same, except they're shifted. Those spectral lines, not here, but this one shifted. This is longer wavelength to that side. So this is shifted towards the red end of the spectrum. That means it's moving away from us. All of them moving away from us. And the bigger the shift, the faster it's moving. And so from that information, I won't get into the details of it, but from that shift, that red shift, we can tell how far away those galaxies are. That's how we get the distance to those things.
How do we know they're not going in the other direction?
Because they're red shifted. If
But
they
you
were,
started with red and you're shifting back towards the ultraviolet.
then they would be blue shifted.
Yeah, but if you started, that was your first one.
Right. Well, yeah, I see what you're saying. So we know hydrogen and oxygen, we can produce those spectra in the lab. So we know what wavelength that line of hydrogen should have if it's not moving when it's stationary. But the problem is every time we see those hydrogen lines in every galaxy over about 3 million light years away, every galaxy is red shifted. There are none that are blue shifted. Yeah. So we know they're moving away. The universe is expanding. It's quite amazing when you think about that. So you want to demonstrate that to yourself? Had a rubber band around my wrist. I just broke it. Anyway, that's all right. Take a rubber band. Draw. That's right. You have good imagination. So take a rubber band and draw it. Oh, okay. Here we go. So now you still have to use your imagination. Take the rubber band and draw a wave on it. You know, start it. And then stretch it. Okay. What happens? Yeah, the wave gets longer wavelength, right? And that's exactly what's happening in the universe. These waves left there 12, 13 billion light years, 12 or 13 billion years ago, but the universe itself has expanded and stretched the wave, just like the rubber band. I know. That's so cool. But yeah, it's just amazing that they
No
can.
gesture on it.
What's that?
No gesture there.
No quizzes. But everybody gets a PhD at the end.
This is what it looked like 13 billion years ago.
Let's see, this one, that one right there.
So
Yeah.
we're kind of late to the party, right? To
Yes.
see what's going on. How can we infer what might be happening now if we're looking at a picture that's 13 or bajillion billion?
You're right, exactly. That's why we're going to bring things closer to home in just a minute here. Okay, so we can see what's going on now, quote unquote, in this case. But what we're trying to do here is to look back in time. So we're fairly certain the universe started as a Big Bang 13.7 or 0.8 billion years ago. What happened since then? I think I may have a slide on that. Yeah, here we go. So this is what we're doing. We think Big Bang and then a plasma of all sorts of stuff, dark ages, here. So these galaxies that we're looking at are way back right here in time, very near when the first stars and first galaxies formed. So that's what we're trying to see right now. Hubble and a few other telescopes could only see back, maybe to within 1 billion years of the Big Bang. This one's looking back to about 1 million years after the Big Bang, roughly. Yeah.
So the image you have right now on the screen
Yes.
is looking at a slice, right?
It's a cartoon to try to give you some idea of the timeline of the universe. Yeah.
Would it, in reality though, would that Big Bang have produced something that was a whole 360?
Yes.
So
Yes.
we're only really thinking about our section,
Yes.
but there's the whole 360.
Yes. I'm gonna blow your mind even
You've
more.
already done it. I don't know how there's not much left to blow.
I love how you keep using the word only.
Right, exactly. I mean, take that thought one step further. Supposing I look out this way and I see a galaxy that's 13 billion light years away. Isn't that looking back in time when the universe was smaller? It's expanded since then. So we're looking back at a smaller universe.
Is that like maps in the time-space continuum?
Yeah, really. Now do the same thing this way. And I see a galaxy 13 billion light years out there. Aren't I looking back in time when the universe was smaller? So no matter where I look, I'm looking back towards a smaller universe.
I have an upgrade if you want.
Yeah, I think I just short.
I love thinking about that. I just love it. Anyway. Okay, so when we look at nearby galaxies like the Andromeda Galaxy and so forth, we're looking at these things right in here, newer kinds of stuff. Light that's left there, you know, a million light years ago. When we're looking at what JWST is looking at, we're looking at those galaxies and first stars to see how they developed, what might have been the trigger for those. Okay, so back to that first picture that we started, we mentioned these arcs kind of thing. Well, there's some more weird stuff going on here, all right? Gravitational lensing. So what's happening is there's a very distant galaxy out there, and then this cluster of galaxies, those fuzzy things that you could see in the middle of the picture. And the light actually gets bent around just gravity from that cluster, bends the light around, and we see some of the light from that distant galaxy. And that's what those arcs are here and here, a distant galaxy way in the background. But what the spectra can do for you is they manage to get a spectrum of both of those, same spectrum, same distance. So these two arcs are from that one galaxy way in the distance. Quite amazing stuff.
So there's a lot of oxygen in the universe.
Yes.
Hot air.
No, that's
It's cold.
my prerogative, hot air. Yes, there is. All right, let's bring it closer to home because I'm sure I'm running out of time here. In case, here's just some of the other gorgeous pictures from JWST. This one is the Cartwheel Galaxy. So this is a galaxy about 100,000 light years across. And I think it's something like 500 million light years away, closer to home, only 500 million years. Two other satellite galaxies. This is a lot of star formation going on around the edge there, probably because these guys passed through each other. They collided and are now going out the other side, triggered a lot of star formation. Stephan's Quintet. This galaxy is in the foreground, but these four galaxies here and a fifth one up top right there are colliding. Not that one, but you can see the misshapen parts of it and so forth, which happens when galaxies collide. This is looking much closer to home, 2,500 light years. So now we're in our own galaxy. And what we're seeing here is a star dying. And this is what's going to happen to our sun in, 5 billion years or so. So again, hang around if you want to see this. But what happens is our star swells up. It puffs off some layers of itself. And that's what we're seeing right here. In this case, there are two stars at the middle, which JWST was able to resolve that there are actually two stars there, and they're orbiting each other. And that's why the funny configuration here is just those two stars. Here's another one that just blew my mind, okay? This is a star, not all that far away, in our own galaxy. I think it's about 1,000 light years away. but it's got a planet that passes in front of it. And when that happens, you get a dip in the amount of light coming from that star. It's just being blocked, okay? But this planet's got an atmosphere. So the dip isn't straight down and across, it's doing this. And that's because of the atmosphere. And as a result, you can get a spectrum of the atmosphere around that planet that's going around another star. Just absolutely amazing. And look what they found. These are those spikes that we saw in the spectrum, kind of thing. Water vapor. That planet, it's big and hot, so I don't think there's any life there, but there's water vapor there. So now, this is one of the first images released. Imagine what JWST is going to do as they continue their investigations. I think we will find Earth-sized planets with signs of biological activity, maybe. We'll have to look for water and oxygen and formaldehydes kind of thing, organic materials, but I think we're going to see that in this case. Mr. Osborne, may I be excused? My brain is full. No, not yet. This image was just released yesterday. So this is Jupiter, and it's showing the great red spot here. It's not red because in all of these pictures, our friends, the artists, help us out to portray the pictures. We can't see infrared. So we got to show you somehow what's bright and what isn't. And that's what our artist friends do for us. These are aurora on Jupiter, northern lights and southern lights kind of thing. So a lot of more interesting stuff coming out. So I think JWST has done its job. You know, we're seeing distant galaxies here that are near the birth of the universe. We're seeing these, we're able to measure the distances to these galaxies that are so far away. We can look nearby and we can see star formation going on. We can see planets forming and the atmospheres of planets giving us maybe hints as to how life forms. Quite remarkable. Nearby dying stars and our own planets, Jupiter and so forth. Let me stop there to see if you have any more questions. Oh, lots, yes.
I have a question about the satellite itself. I happen to be wearing my honeycomb earrings today
I love
in
it.
honor of saving bees. But I noticed that a lot of the shape of the telescope was honeycomb shaped, or no, pentagon, I suppose,
Yes.
or hexagon. Is there an intentional? I mean, there must be an intentional purpose for that.
Yes. Whipping right back to the beginning here. There we go. Yeah, there's two purposes to having that honeycomb shape. One is to be able to fold them because you had to get them into the nose cone. But the other is each of these is independently controlled. And so you've got plungers and sensors that aim each of those mirrors individually. And so that was the very first thing they had to do once they got it unfolded, is take a picture of a star, and you got, I think there's what, 18 of them there or something. You got 18 images. So now you have to focus them so that all 18 images come to a point. Now you know you got it folded. So yes, good observation and good question.
What is the projected lifespan?
Oh, that's a good idea. A good question. I'm gonna suggest about 10 years, but it already got hit with a meteorite. And so if any more of those come along and hit at the wrong spot, it could be shorter than that.
Did you hit one of the years?
I think it hit, I don't know. Yeah. I would think, I mean, the first thing is it would hit one of the sun shields. And that again could ruin it if you don't have that sun shield in place. You can't cool the telescope enough. And, so yeah, I'll look that up.
I read that report that it had been struck and they were concerned about the quality of the images.
Yes.
And I thought,
Yeah.
what do you get? There must be just you know, we're talking, the numbers you talk, and you think about it, so you, I think how many pieces of space trash or things that must be flying around.
Yes, right, exactly.
Well, we're going to have you stay as long as you're able, and I'm sure there'll be more questions and
I agree.
tests and all of that. Don't forget to put your money in for the slide. But we have a gift for you, so it'll bring you back to home here a little bit for being out in the sky. But these are award-winning photos from Golden Valley. We made them into note cards, so you can
Wonderful.
enjoy Golden Valley when you're sending out notes and that.
Thank you so
Thank
much.
you so much for coming. Going to say the four-way test of the things that we think, say, and do. First,
Is it the truth?
second,
Is it fair to all concerned?
third,
Will it build goodwill and better friendships?
and fourth,
Will it be beneficial to all concerned?
and fifth, if we wanted to add it,
Have
have
fun.
fun. Thank you.